Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 61, and we will be today looking at characterization and modeling of 22 nanometer FDSOI cryogenic RF CMOS. Now let's see the outline of the lecture will be. Typically we will be looking at the meaning of FDSOI technology, which is FDSOI primarily means fully depleted silicon on insulator. So, when we say FDSOI, we refer to as FDSOI. It means fully depleted silicon on insulator, right? And typically this has been a go-to technology for those cases where your leakage requirements are very minimum, or you want to go for an ultra low power design, because this is silicon on insulator. You typically have a very large insulator at the substrate side, which allows you, or which does not allow the flow of leakage current through the backside of the device. We will be also looking at the DC characterization of the fully depleted SOI technology, and finally we will be concentrating on RF characterization of a 22 nanometer FDSOI in cryogenic region. When I say 22 nanometer, it basically means the channel length of the fully depleted SOI which we are proposing in this lecture. So, before we deep dive into actually the characterization process of a 22 nanometer, on the right hand side if you see, you will have the actual structure of device. This is basically a TEM image, and in this case if you look very carefully, we have a substrate here, right? And then you have a box layer. Box basically means what is known as a buried oxide, right? So, this is a buried oxide which is typically a thick oxide, maybe a silicon dioxide, and this actually prevents your backgate leakage. The substrate, which in this case is silicon, which we are using. So, this is SOI as silicon on insulator, and this is my silicon, this is my insulator. So, that is the reason it is known as a silicon on insulator, because you have an insulator layer and over that you have the silicon active area from where you are actually fabricating the device. This is 22 nanometer, and typically we use silicon channel for NFET, and we also use silicon germanium channel for PFET, where we use approximately 20 to 25% of germanium content. Why is it so? Is because typically if you remember, your NFETs will have electrons as the majority carriers, and since electrons already have a large amount of mobility available to it, its overall current is therefore typically large. So, if I have an SOI based NFET having a silicon N channel MOSFET, then its current is suppose X. However, if you take everything same for a PFET, being the mobility being relatively smaller, you will always get the less amount of current for PFETs, right? Now, if you want to match the current, also referred to as ISO current. So, there are two types of design which we do. We do ISO current, which means the same current, and then we have an ISO power, and we also have ISO area. So, these are the three methods by which we characterize a FDSOI CMOS. ISO current means both the devices NMOS and PMOS have the same current flow, and ISO power means they might not have the same current, but they surely have, they dissipate exactly almost the same amount of power. And ISO area means the layout area, which is silicon, the active area of silicon is again the same, right? Why do you use silicon germanium? Because silicon germanium is primarily not a heterostructure, but it's a silicon plus about 25% germanium molar fraction device. What it does is it creates stress within the silicon, right? Why? Because germanium typically has different structure as compared to silicon in terms of its area occupancy, and therefore when you insert germanium within the silicon lattice, it stresses the overall content of the silicon. When it does that, it actually increases the mobility of the holes, right? And when the mobility of the hole becomes almost equals to that of electrons, even for the same device structures, you will get ISO current characterization. So, this is one thing which we should learn. Then how it was fabricated was, we are taking it from this paper. This paper is primarily was published in IEEE Journal of Exploratory solid state computational devices and circuits, right? And this was published in the year 2021, right? And it starts from page 184, right? So this is the literature from where this has been taken, and you can actually go back for more deeper study into this area. Now, the devices which these authors have fabricated was using a high K material gate process, high K metal gate process, right? The dielectric constant of the metal gate which they are using is relatively very high. So if you look at the right hand side here, you have this high K metal gate here, which is there over the silicon channel. This is an NFET here. This is an NFET, and the right hand side is effectively a PFET, right? So I have a polysilicon here, and I have a high K metal here, and this is my silicon here, and this is my silicon which is kept here. This is the silicon germanium channel for PFET, and this is the silicon channel for NFET. And these are my source and drain region, which is effectively given like this. Now, the devices are fabricated in such a manner that their body are ultra thin, and the semiconductor channel is very lowly doped, and the channel dimensions are very small, 6 nanometer around. The box thickness, which is this one, is approximately 25 nanometer. This is the bulk oxide thickness, nanometer, and the CET, the capacitance equivalent thickness of high K dielectric, is approximately 1.3 nanometer, right? So just to give you a brief insight on why FDSOI happens to be a major stay in cryogenic electronics is that when you do at 4 Kelvin cryogenics, when you do a 4 Kelvin cryogenics design, they are employed in what is known as a Josephson junctions, right? And this Josephson junction is used for what is known as a single flux quantum logic, right? And what it says is that this basically promotes your operating power to be at very low value, and they can be used for high performance cloud computing systems because of exceptionally low power which is there for an SFQ circuit. And when you push it down to cryogenics, the power dissipation further drops down to a very low value. So this is the basic advantage of using an FDSOI device because of least amount of leakage available to us. Now why RF frequency? Why is it used at RF frequency? Now it is equally important to complement your any of these devices, superconducting devices, logic technologies, with compatible high bandwidth and low latency technologies. Low latency technologies means almost real time technologies has to be incorporated in the design. For example, if you are using it for a 1.3, let us suppose you are incorporating a 1.3 gigahertz technology. This is for 1.3 gigahertz DRAM technology, right? DRAM technology, and it is embedded in cryo. Then this technology will be quite useful in designing a DRAM structure. But that DRAM is basically meaning dynamic random access memory. They are also used in the cryogenic DRAMs are used in the same thermal plane as the Josephson junction devices. So you don't have to specially make a cryo chamber for doing it. You can actually have the same cryo chamber where you can embed DRAM with that of the Josephson junction for acting as a memory element. Okay. Now, if we look at the gain, the gain of these devices are typically very large, right? They are typically of the order of 400, means 4 into 10 to the power 2. So volt by volt gain, if you consider, it is 4 into 10 to the power 2 which you get, right? And so the conventional gain is typically very large, and it also allows you to keep the bandwidth of the order of few gigahertz, right? And that is quite an interesting idea. So placing the cryo CMOS circuitry, if you place the cryo CMOS circuitry very close to the proximity of the quantum processor, which we have already discussed in our previous lectures, you can actually have much advantage in terms of low latency, and not only low latency but scalability, which means that if you are designing n qubit system and you want to grow that to a 3 and a 4 n qubit system, it's easily scalable because of the fact that both the devices are at the same temperature region. So that's the reason this study or this knowledge of having a 22 nanometer FDSOI is quite important and interesting. With this knowledge or with this idea, let us start with looking at the transfer characteristics of the device, right? We will look into the transfer characteristics of the device for different VDS value. Transfer, when I say, it's basically ID versus VGS drain current versus gate voltage for varying values of the temperature. Okay. Now, this is basically an ultra thin body, right? So it's ultra thin body, UTB, ultra thin body device, and the commercially available FDSOI CMOS, typically at 22 and 28 nanometer tech node, right, have been investigated at around approximately 4.2 Kelvin temperature for this paper. They have actually looked into device variability issues and self heating. So, both self heating effects and device variability effects have been taken into account. Both the devices have been taken into account while designing this issues. The paper actually has looked into the RF performance with respect to temperature and gives you a much better result beyond a particular point. At 300 Kelvin, the results are as comparable to CMOS, but at lower down the temperature, at cryogenic, you get a very much good design. So, if on the right hand side, if you look very carefully, let me rub this portion here so that it's easier for me to do that. So, let's look at the right hand side portion, right. We have a transfer characteristics for an 80 nanometer FDSOI, and one is operated at 50 millivolts, right, and the right hand side is operated at 1 volt. So, this is operating at 1 volt VDS and this is operating at VDS equals to 50 millivolts. So, one is VDS. So, if you remember from your basic FET theory concepts that the device which you design will be insaturated if the VDS value is greater than VGS minus VTH, right. So, when you say VDS is greater than equal to VGS minus VTH, we define that to be a saturated. So, typically this figure, if you count, is basically the saturated one, and if you look at this figure, this is almost at subthreshold or even much smaller than that, right, the transfer characteristics. And what the paper has done is they have given you NMOS, PMOS for both unsaturated as well as saturated state and for varying values of temperature from 5.5 Kelvin to 300 Kelvin. If you look very carefully in all these figures on the right hand side, this is the 5 Kelvin, and this is, as you move towards this side, the temperature goes on increasing, right. So, as you can see very interestingly, that this is a log scale. Please understand the current scale is basically the log scale, right, because there is a large increase in the current for a small increase in the gate voltage, whereas my gate voltage scale is basically a linear scale. So, I have a linear scale here and I have a log scale here, right. And if you look here, let us take up the case where LG is equals to 18 nanometer and your drain voltage is 50 volts and you are operating at somewhere near say 0.25 or 0.3. As you can see here, if you draw a line, straight line cutting these axes, as the temperature increases for the same value of gate voltage, the current is much higher, right. And it is true also, it will be true like that. But the interesting case happens that when you go to when you make your gate voltage higher and higher, there is sort of a crossover point which happens here, which means that the lower temperature region of ID actually becomes more than the high temperature region, somewhere around 0.5 to 0.6 volts, right, 0.5 to 0.6 VGS value which you get around the subthreshold region, or just near the threshold. There is a swapping of the currents between the thing, and the swapping is more prevalent in NMOS as compared to PMOS. You see, if you compare the swapping here and here, you see the swapping is more in case of NMOSes in this case, right. Now, the temperature is varied from 5.5 to 300 Kelvin, as I told you earlier. At cryogenic temperature, of course, your very steep subthreshold slopes are observed. You see, they are almost straight line. So, your subthreshold slopes are relatively much sharper, right, and you will get much better switching at subthreshold characteristics as compared to post-threshold characteristics. Now, this is for 50 millivolt concept. Now, the improved drain current drive observed due to reduced photon scattering beyond 0.5 for a low temperature design, right. For a low temperature design, it is beyond 0.5 which is happening. Now, let us concentrate on the fact when LG equals to 18 nanometers and your drain to source voltage is 1 volt. Obviously, you will see that for all the practical purposes, If I draw a line of say 0.25 in this again, right, and if I draw a line, you will see the current in this case was around 10 to the power minus 3, whereas in this case it is approximately slightly more than 10 to the power minus 3, which means that as the drain to source voltage increases, the current for the same amount of gate voltage and temperature increases, which is expected also because you do have larger drain to source voltage, implying that your drift velocity will be larger, which will entail a larger drain current in a much better manner. That's the reason you see the drain current is somewhere between 1 milliampere to 10 milliampere is the value here, whereas it is much lesser than 1 milliampere when you're operating at a much lower drain to source voltage. Similarly, you also get a better ion to I-off ratios in case of the 1 volt supply when you do it at 5.5 Kelvin as compared to 300 Kelvin, right? Your I-off, and that's the major advantage when you do at cryogenic, your I-offs are very much reduced drastically when you do, especially FDSOI, and that too at low temperature. And therefore, a major parameter for all of us in the figure of merit is basically ion by I-off. So, when ion by I-off actually becomes larger in this case whenever you are operating at a 5.5 Kelvin as compared to 300 Kelvin. Now, let us look at the output characteristics in this case, right, and let's see, we will come to Y parameter and Z parameter later on, but let us come to the output characteristics. Now, on the right hand side, if you see, the figure is between ID versus VDS, and again here ID is not log scale, it is a linear scale, ID versus VDS for NMOS and PMOS both. So, what I am doing is, this is my drain current and this is my drain to source voltage, this is my NMOS and this is my PMOS here, and I am doing it for T equals to 300 Kelvin down to 70 Kelvin around liquid nitrogen, and then we go down to liquid helium, which is 5.2 to 5.5 Kelvin range, and I am using my overdrive, which is VGS minus VTH, vary from 0 to 1 volt with a step of 0.25 volts. You got the point? And as you can see here, it is done at a step of 0.25 volt from 0 to 1 volt. So, I will get 0, then overdrive will be 0.25, then you will have 0.50, 0.75 and then 1 volt. So, there will be 4 graphs related to it, related to this value here. This red colored graphs, dotted curves is for 300 Kelvin, and the blue ones which you see here, the blue ones are actually overlapping over each other. Let us only concentrate on the NMOS. Then the blue ones are almost overlapping with respect to each other. As you can always see that your saturation value of the current at 300 Kelvin is relatively smaller as compared to that at 5.5 and 70 Kelvin, right? And typically NFET shows approximately 37% IDS or drain current improvement at 5.5 compared to 300 Kelvin, whereas PFET shows a 60% drain current improvement at 5.5 compared to 300 Kelvin, right? And this is a major sort of advantage which you get in case of a low temperature, that your saturation currents are relatively larger in this case. This is one thing. The second thing which you can see is that as you make your overdrive larger and larger, the CLM effect is almost independent of the overdrive to a larger extent, right? So how do you find the CLM? CLM is basically the slope of this curve at saturation. This is almost the same, like it does not matter too much what is happening in this case, right? And it's almost the same. But just to reiterate the point, and the takeaway from this slide is that you typically gain a large amount of current when you operate at about 5.5 Kelvin as you compare to 300 Kelvin. Now, let us look at the DC characterization of FDSOI. When I say DC characterization, I need to find out the NMOS threshold voltage and PMOS threshold voltage. On the right hand side, if you look, it is basically I am plotting threshold voltage on the y axis and temperature on the x axis, both on the linear scale, and I am trying to plot the value of the threshold voltage with varying temperature, right? And the solid one, this one is typically for 50 millivolts, right, and this one is for 1 volt. So, with 1 volt, first of all, you see very clearly there is a drop in the threshold voltage, and this is basically to do with Dibbles actually, right, drain induced barrier lowering, right. So, what will happen is that you will have a reduction in the threshold voltage with increase in the value of drain voltage in such a scenario. Now, this is for LG equals to 18, right. Qualitatively, the graphs will not change if you make the the gate length, the technology node move from 18 to 22 or 22 to 28. Remains almost the same qualitatively. Quantitatively, there will be always a change. If you look very carefully, then the difference between the threshold voltage between this point and this point, this is 0.35 approximately, and this is approximately 0.45. So 0.45 minus 0.35, which I get, is approximately 0.1 volt I get. So 0.1 volt change I see in threshold voltage by virtue of drain voltage change of 1 to 50 millivolts, right? Okay. Now, however, an important criteria or concern is also that as you reduce the temperature, the threshold voltage increases, and the increase is almost qualitatively and quantitatively same for both NMOS, PMOS and 50 millivolts and 1 millivolt. Now, basically the threshold voltage increases because of an increased value of the Fermi potential at low temperature. Your Fermi potential actually shows a higher value, and therefore, in order to invert a channel, you require a larger gate voltage to do that, right? Now, if you look at PMOS, the PMOS threshold voltage is obviously larger as compared to an NMOS threshold, but the difference is approximately the same between 0.1 volt and 50 millivolt. And since Dibble effect is more to do with the distance between source and drain, therefore, the difference of threshold voltage at 50 and 1 volt, 50 millivolt and 1 volt is almost the same for both NMOS and PMOS, right? It is, if you look very carefully, this is 0.1 volt here, and this is also 0.1 volt here. So the difference is primarily because I am still taking 18 nanometer as my gate length in both the cases, right? And that gives you a brief idea about how the cryogenic temperature enhancement takes place. For PMOS, there is a shift in the threshold voltage is larger for silicon germanium than for NMOS, which is about 160 millivolts, and this is 120 millivolts, right? But qualitatively, they look same in both the cases. Now, if you remember properly from our very early days of this lecture series, we were looking at the backgate bias, right? We are looking at backgate bias. Now, if you remember forget about cryogenics, for a simple NMOS device, when you give a backgate bias, the threshold voltage changes, right? You all know this point. This is also referred to as a substrate biasing, or VSB or VBS value, right? Now, in case of FDSOI, since your backside dielectric is very large, you need to give a relatively larger substrate potential in order to change the threshold voltage, right? And therefore, even at cryogenic temperatures, FDSOI backgate biasing works very well, effectively, right? As compared to a bulk MOSFET. Now, I have seen already that with increasing value or decreasing value of temperature, threshold voltage increases, right? So, if I give a positive bias, N-type MOSFET in this case, if I give a positive bulk bias, it will try to restore the value of the threshold voltage to a lower value. I will try to explain this by a simple figure here, that you see, with decreasing temperature, we learned in the previous slide that as my T goes on decreasing, my threshold voltage goes on increasing, right? So, at say around 5.5 Kelvin, right, your threshold voltage increases by say plus 0.1 volt, let us suppose 100 millivolt is the increase, let us suppose. Now, you need to give a positive bias at the backgate for an NMOS, so that the threshold voltage drops by the same factor as it has increased by virtue of temperature. So, this is a methodology which many circuit designers use in case of FDSOI in cryogenic, that they try to apply positive bias on the backside, and when they apply a positive bias, they tend to make the threshold voltage go down, and whatever increase is happening because of temperature variation can be offset by increasing the value of substrate voltage. And that is what is written as bullet number point number 2, that at 5.5 K, if you apply substrate bias of plus 2 volts, it can restore the value of the threshold voltage, which is the same value as 300 Kelvin. Now, the backgate bias efficiency given by gamma, which is del VTH by del VB, with change in the threshold voltage by change in the substrate bias, it almost remains constant across all the temperature, which means that it is 80 millivolts per volt, which means that for every 1 volt change in the value of VB, I will actually get a decrement of 80 millivolts. So, if I do 2, I will get 1.6 millivolts, sorry, 160 millivolts. So effectively, that increased value of threshold voltage is being offset by the increased value of the bias, the positive bias which you see here, right? With positive bias value is plus 2 volts, which I have already shown you here. This is plus 2 volts. And the idea is it remains almost constant. So, if you look at the graph on the right hand side, where I have plotted the threshold voltage with respect to the bulk bias, as you can see, as the value of bulk bias goes on increasing, the graph actually starts to go down, which means the threshold voltage actually starts to go down. As you can see here, for 0.5 it is approximately 0.18, and as you make it to 2.5, which is 2 volt increase, it is approximately equals to 0, slightly more than 0, which is about 160 millivolts difference, 150 to 160 millivolt difference is there. This change in the voltage is referred to as the backgate bias efficiency, also referred to by gamma in this case, right? And that gives you a brief value of how I can actually manipulate the value of the threshold voltage. Now, let us look at the subthreshold slope variation. Subthreshold slope actually improves with respect to temperature decrease. What is subthreshold slope? Basically, it means that the amount of voltage you need to give on the gate side to make a 1 decade change in the current, drain current, right? And that is important, that you should keep that was as low as possible. At 300 Kelvin, the value which you already know is actually 60 millivolt per decade for a FET technology. However, as the temperature drops down, subthreshold slope reduces and saturates to around 20 millivolt per decade because of the DIT or the interface trap charges. Now, since there are interface trap charges, even if I reduce the temperature, I cannot release the traps, the objectives which are kept in the trap very easily to the output side. And since I cannot do it, my subthreshold slope remains always constant at approximately 20 millivolts per decade. Similarly, a proximity of the Fermi level to a high trap density region and a sharp Fermi level function at cryogenic causes higher CIT. CIT is interface trap charge density, and CIT is basically your fixed charge density which you see, right. Now, rather than going into details of it, I will just give you a brief idea. If you look at 4.2 Kelvin, the Fermi function, it is almost like a delta function which you see. As you move your temperature to 300 Kelvin, it becomes almost like this, something like this it becomes, right. Which means that at 4.2 Kelvin, because of incomplete ionization as well as because of large amount of CIT and DIT, your subthreshold slope saturates at 20 millivolts. That is what you see here, right. As the temperature reduces, subthreshold slope reduces for sure, and somewhere around low temperature, around 70 Kelvin or 50 Kelvin, it saturates to a value of 20 millivolts per decade, independent of whether it is an NMOS or a PMOS. Because this is for NMOS PMOS with LG of 18 nanometer and VDS of 1 volts, and this is for both the devices NMOS and PMOS, correct. And this gives you a basic idea about the characterization of the DC characterization. Let us now look at another characterization. This is the transconductance characterization. And transconductance basically means del ID del VGS, which means that if I give a small change in the value of gate voltage, how much change I see on the drain current. Now, if you look here on the right hand side, I am plotting the saturated value of the transconductance with respect to gate length here. So, saturated value is transconductance is on the y axis and my gate length is on the x axis. As I reduce my gate length, the saturated drain current slides to increase and the GM SAT actually saturates itself beyond 30 channel length, right. And it scales with the channel length at the rate of Lg to the power minus 0.3, and the saturation is observed for gate length of less than 28 nanometer, and the performance improvement is only due to the reduced phonon scattering which you see and a better contact resistance, which means that you might not be able to gain in terms of amplification too much below 30 Kelvin, because your GM is getting saturated. When GM gets saturated, GM times RD, which is the voltage gain, also gets to get saturated in this case. Now let's look at the PMOS saturation here, and this is quite interesting. PMOS does not saturate. GM sat for PMOS is not saturating with respect to temperature. It is almost going on increasing as you make your channel length go lower and lower. And not only lower, your lower temperature, and but what you see is that as the temperature goes on reducing, the value of GM sat also goes on increasing. And this is because of a lower contact resistance in silicon germanium source drain region as compared to NMOS, right? And therefore, unlike NMOS here, the GM sat actually starts to increase even for a smaller gate length. So this is the overall feature of cryogenic FDSOI DC characteristics. What we will do in the next turn is we will look at the RF characteristics of FDSOI, and let me recapitulate what we did in this lecture series. In this lecture series, we try to give you an idea about the FDSOI technology, what is the meaning of fully depleted SOI technology, and how can I use it for, at least in the first lecture, how do I use it for DC characterization of a cryogenic FDCMOS technology. With this, let me thank you for your patient hearing. Till we meet next time, goodbye.